Section 5.5, we're going to talk about other bases. What do I mean by other bases? Not E. So far, we have two functions that we've looked at a lot. We have the function f of x equals ln x, which quite often is referred to as log base e of x. And we have another function, in particular its inverse, e to the x. So this g of x function, this is an exponential function with base e, and ln x, this is a logarithmic function, base e. And at this point in our life, those are the only logarithmic and exponential functions we've talked about. But of course, you could have other bases. You don't have to have base e. In fact, sometimes it's very helpful to have other bases for exponential functions. What kind of other bases are helpful? Pi, maybe, but not usually. I've never seen a good application that has base pi. 10 is a very useful base. Why do you like base 10?
I just heard of base 10 before. Base 10 is counting numbers.
Our whole number system is based 10, isn't it? For example, you have 10 to the 0 is 1, and then 10 is your tens position, 10 squared is your hundreds position, 10 cubed is our thousands position. Our whole number system is base 10. So base 10 is a very helpful base. Any other bases that are useful? 2, 8, and 16 are useful ones for certain people. For computer science people, why 2, 8, and 16? 8 not so much anymore.
Binary, octal, and hex.
Binary, octal, and hex. That's correct. Those are used a lot in computer science. You know that? Binary is base 2, octal is base 8, hex is base 16. And then there's 32 and 64 also with newer computers. Any other useful bases? Base 1/2 is actually a useful one. For example, in one of the labs that we've been working on, we've been using half-life. And we've used the function p equals p0 e to the kt. And how did we figure out the number k? We had to know something about the half-life of the element you were working on, didn't you? So if your half-life was 5,700 years, you would do something like this. 1/2 p0 equals p0 e to the k times 5,700 if you were dealing with carbon-14. And you would solve that equation, and that would give you your k number. However, if you're working base 1/2, life is a lot easier. In base 1/2, the same formula would be p0 1/2 to the t over 5,700. I don't need to figure out the k number. Why, if the half-life is 5,700, is our formula p0 1/2 to the t over 5,700? Without having to do any work at all. Well, what happens if I take t equal to 5,700 and plug it in? What's 5,700 over 5,700? What's 1/2 to the 1? 1/2. So we would have 1/2 of our starting amount. So if you're dealing with half-life problems, using base 1/2 can be very, very useful. It makes the formulas a lot more simple to deal with. Okay, so here's what we're going to do. We're going to make two definitions. We're going to define log base a of x in terms of ln. So for us, log base a of x is going to be ln x over ln a. And we have to have a little rule here. A has to be a positive number, and a cannot be the number 1. How come A has to be a positive number? We can't use negative numbers in ln, and right here I have ln A. I can't use any negative numbers. ln is only defined for positive numbers. How come A can't be the number 1? Ln of 1 would be 0, and we'd be dividing by 0. At the same token, we're going to define A to the x to be e to the a ln x. Why does that second definition make sense? True, if you were to take the natural log of both sides, it would be equal, but there's an easier explanation. What could I do with this a right here in this ln? The a would go in, it would become a power. And then what happens with the e and the ln? They cancel and you're left with... Oh, I wrote those backward. That's got to be e to the x ln a. I flipped them backward. Alright, so that x goes in and we get a to the x, and then the e and the ln reduce. And we get a to the x. I wrote that backward, that was bad. Once again, we have to have a has to be a positive number. A cannot be 1. How come a has to be a positive number? Because we have an ln and we can only plug positive numbers into ln. How come a cannot be the number 1? Natural log of 1 is 0, so this e to the 0 thing would just be the number 1, and that's not a very interesting function, is it? Just a straight horizontal line. Not very good. Alright, and then we have a fact. A to the x and log base a of x are inverses. Alright, so now let's do a little calculus. Let f of x equal log base a of x. Then f prime of x is what's the derivative of log base a of x? Over x. No, you're close. 1 over x is right. Well, remember how we defined log base a? Log base a is ln x over ln a. What's ln a? It's a number, isn't it? So you could write log base a of x. Our definition was it's ln x over ln a. So I'm going to write this as 1 over ln a times ln x. ln a is just a number, so 1 over ln a is just a number. So what's the derivative of a number times ln x? What happens to this number? Yeah, I mean, if I had y equals 5 ln x, and I asked you to take the derivative, what would you do with that 5? You just leave it there because it's a multiplier, right? So y prime would be, you would have the number 5, and then you would take the derivative of ln x. The derivative of ln x is 1 over x.
1 over x ln a.
That's right. This 1 over ln a is just a number. It's going to stay just like the 5 did. So the derivative is going to be 1 over ln a times the derivative of ln x, which is 1 over x. So this is typically written as 1 over x ln a. Questions on that? Alright, so g of x is log base 6 of x. What's g prime of x? One over x ln 6. That's correct. H of x is log base, I don't know, anybody got a number they like?
If somebody says 13, I'm going to be
31 of x squared plus 2. What's h prime of x?
Times, wouldn't it be, because you have to take the derivative of that inside, times the inside, and then ln of 31. Do you know what I'm saying?
I know what you're saying.
I just don't know how I'm
You got the wrong thing on bottom. The 2x
Oh, that'd be on top.
goes here. That's the derivative of the inside. So you're right. You need to use the chain rule. So it's going to be 1 over, what goes down on bottom?
X squared plus 2.
You leave that alone, don't you? That's x squared plus 2. And then because this is log base 31 and not ln, we also have an ln 31 on bottom. And then we have to multiply by the derivative of the inside. We have to use our chain rule. The derivative of the inside would be 2x. Questions on that? Okay. One more of these, and then we'll talk about e's. How about f of x equals, I don't know, how about x squared log base 3 of 9x. What's the derivative? Absolutely product rule, because we have x squared times log base 3 of 3x. We use the product rule. We take the derivative of the first one, that's 2x. We leave the log base 3 of 9x alone. Plus, I leave the x squared alone. And then I need to take the derivative of log base 3 of 9x. What's the derivative of log base 3 of 9x?
9 over 9x.
Very good. It's 1 over 9x ln 3. The 9x, you leave the 9x alone. That goes on bottom. You need an ln 3 because it's a log base 3. And then you need the derivative of the inside. The derivative of the inside is 9. And obviously you can reduce the 9s there. Questions on that? Alright, now let's look at derivatives of exponential functions. F of x is a to the x. We define that to be e to the x ln a. Which tells me its derivative is, I'll forget about this a to the x for just a minute. How would you take the derivative of e to the x ln a? Can you take derivative of e to a power?
Times e.
The e thing stays just like it was, right? You're going to have e to the x ln a, and then you take the derivative of the power. What's the derivative of the power? ln a. Why ln a?
That'd be like the number.
Again, that's a number. So this is a number times x. The derivative of a number times x is the number. But now we use the fact that e to the x ln a, that was just a fancy way of writing a to the x. So the derivative of a to the x is a to the x ln a. Just like the derivative of e to the x was e to the x ln of e. But we didn't write ln of e because ln of e is the number 1. It's number 1. ln of e is 1. Okay. So the derivative of a to the x is a to the x, except you have this little correction factor because we're not dealing with e to the x. Alright, so once again, once you know that, that opens up all sorts of new rules for you. What's the derivative of 7 to the 6x? You're missing one thing. ln 7. Correct. The derivative of 7 to the 6x, the 7 to the 6x stays alone. You take the derivative of the power, that's 6, but then you need this little ln 7 because your base is not e. Anytime your base is not e, you're just going to multiply by ln 7.
So that's going to be ln of your base every time?
It's going to be ln of your base every time. Correct. Ln of the base right here in the rule. Alright, h of x is, I don't know, x to the 5th times 5 to the x. Oh, that's a good one. Let's make that one up. I like that one. H prime of x is, what rules do I need to use? I need the product rule. Alright. So I take the derivative of the first one. What's the derivative of x to the 5th? 5x to the 4th. And I leave the 5 to the x alone. Plus, I leave the x to the 5th alone. And I take the derivative of 5x. What's the derivative of 5 to the x?
5 to the x ln 5.
5 to the x ln 5. Alright, so notice those two derivatives of each individual parts are very, very different. For this first part, to take the derivative, you pull the exponent down and you subtract 1 from the exponent.
We can see the answers in that form.
Absolutely. However, to find the derivative of this part, it's completely different. Why? What's the difference between those two functions? Correct. On this one, x is in the base, which means this is a polynomial. So this is what we learned in Calc 1. You bring the power down, you subtract 1 from your power. This one, the exponent is the variable, which means it's an exponential function. The derivative rules for exponential functions are that. All right, so I will see people do this. If I give j of x equals 2 to the x, I will see people write j prime of x equals x 2 to the x minus 1. Is that right? No. When your variable is in the exponent, you don't get to bring your exponent down and subtract 1 from your exponent. That does not work. That one's very wrong. I almost guarantee that on the next test I will see at least one person do that. Hopefully it's not you.
Maybe if you write it more than once, it'll be right.
Maybe if you write it more than once, it'll be right. Write it over and over and over till the teacher's convinced. Good luck with that.
I'm an optimist.
You're not. All right. Other questions on that? Does it give anything special? It gives a big fat 0 on that test problem. Other than that, no. No, it's just very wrong. It doesn't do you any good. Very wrong. All right, do you remember last time we talked about doing U substitution and talked about the integral of e to the kx, where k was just a number. What was the rule for that? What was the antiderivative of e to the kx, where k was just a number?
E to the kx times k.
That would be the derivative. The derivative would be e to the kx times k. We would use the chain rule.
E to the kx over k.
It would be e to the kx over k. Because what we would have to do there, we'd really have to do a u substitution. U is kx. So du is k dx, which means to make my u substitution work, I would have to slip a k in here, which means I'd have to balance it with a 1 over k. So that's where that 1 over k comes from on the bottom there. And of course, plus c. Well, the reason I bring that up is look at what we have. If I want to find the antiderivative of a to the x dx, I can write that as the antiderivative of e to the x ln a. Where once again, what is ln a? It's a number, so it fits this pattern. This is e to a number times x. So the antiderivative is going to be plus c. But e to the x ln a, that's our a to the x that we started with. Alright, so notice the patterns here. When I want to take the derivative of a to the x, I have the a to the x and I multiply by ln a. So it makes sense that when I want to take the antiderivative of a to the x, I'm going to have the a to the x, but I have to divide by the ln a. So kind of a pattern there. That makes sense. Derivative you multiply, antiderivative you do the opposite, so you have to divide. Questions on that? And some fun integral problems. What's the antiderivative of 5 to the x dx? Five to the x divided by natural log of 5 plus c. Questions on that one? Alright. How about the integral of x times 6 raised to the x squared dx? Any good thoughts on that one? U equals x squared. Why do you want u to be x squared? Because then you can get rid of that other x there. When you take the derivative, du is 2x dx. So I need to sneak a 2 in here, 2x dx, which means I balance it with a 1/2. I'm going to have 1/2 integral 6 to the u du. What's the antiderivative of 6 to the u? 6 to the u over ln of 6. That's right. That's 1/2. 6 to the u over ln 6 plus c. So final answer, I'm going to write it as 6 to the x squared over 2 ln 6 plus c. Questions on that? How did the ln get on bottom again?
That first one you did on
the ln came on the bottom because of this rule that we derived last time, that we have to do a u substitution here. U is kx, So I got to sneak in the k, which means I got to divide by the k. Using that formula, k is now the number ln a. So there's that ln a down on bottom. Okay. So again, the pattern is when I want to do the derivative of a to a power, I multiply by ln a. When I want to do antiderivative of a to a power, I do the opposite and I divide by an ln a.
It's like a hidden U substitution you just call right now.
Correct. It's a hidden U substitution in there. So I'll unhide it. How about that? So in this problem right here, u would be x ln a. So du would be ln a dx, which means I would need to sneak in a little ln a right here. So I'd have to balance it with that 1 over ln a. So that's where it comes from. It comes from U substitution. Other questions? All right, let's do one more then. How about the integral? From 0 to pi over 2 of sine of 2x times, I don't know, 151 to the cosine 2x dx. There's a nice number, 151. I haven't used that number very often.
U cosine 2x.
U is cosine 2x. Which means du is negative 2 sine of 2x dx. Alright, so I need to sneak in on negative 2 right there. Balance it with a negative 1/2. The problem with 151 is that kind of looks like absolute value of 5 too, doesn't it?
Yeah.
That's negative 1/2 integral 151 to the u. I don't know that putting parentheses around it helps. It still looks like absolute values. Du.
Draw little feet on the ones.
Draw little feet on the ones. My little ones look like eyes. Oh, anyway. I won't use 151 ever again. That's a bad number. Alright, well, we got to change our limits here. I plug 0 in. 2 times 0 is 0. Cosine of 0 is 1. Then I plug pi over 2 in. Pi over 2 times 2 is pi. Cosine of pi is not 0.
1.
Not 1. Not 1/2.
Oh, wait. Hold on. Circle.
Negative 1. Very good. Cosine of pi is negative 1. Alright, well, we've seen this actually come up a couple times this semester. This is kind of neat with the bigger numbers on top, smaller numbers on bottom, but we've got this negative out front. So I'm going to flip that. I'm going to write this as the integral from negative 1 to 1, and I'll still have a 1/2 out in front of 151 to the u du. So that's a 1/2. I'm going to have 151 to the u over ln of 151. And then I plug in my numbers. Final answer. Looks like it's a 1/2. 151 over ln of 151 minus 1/2. 151 to the negative 1 over ln of 151. Questions on that? All right then, the last thing that appears in this section. Kind of talked about this already, but here it is again. F of x equals 8 to the x, and g of x equals x to the 8. Very similar looking functions, but very, very different in actuality. And of course the derivatives are very, very different. What's the derivative of x to the 8?
8.
8
Doing this one first. The derivative of 8 to the x is 8 to the x ln 8. Okay? And how about this one, the derivative of x to the 8? 8x to the 7. All right. So, if my x is in my base, I do one thing. If my x is in my base, I pull my exponent down and I subtract 1 from my exponent. If my x is in my exponent, I do something very different. I use that rule. What if x is in both places? What if you have the function x to the x? Shenanigans, yeah. Which rule do you use? Do you use the one that has x in the base? Or do you use the one that has x in the exponent?
Do we need a new rule?
We actually need a new rule, that's correct. You don't use either rule. Neither one of them are correct. You hate this? Oh, it'll get better. You didn't say that? Oh, good. I don't know. Why do x to the x?
X has to equal.
I'll give you an example in a minute.
Yeah.
Why you would want x to the x. Alright, so here's what we're going to do. We're going to use our old friend, well, not so old actually, we just learned this a few sections ago. We're going to use our friend logarithmic differentiation. So I'm going to write that as y equals x to the x, and I'm going to take the ln on both sides. So I'm going to have ln of y equals ln of x to the x, and then what can I do on the right hand side? I can bring the power down, that's x ln x, and then I don't have a mixture of my two rules anymore. Now I can take derivatives, and it's something that I know. I take the derivative of each side. What's the derivative of ln y? 1 over y prime, or dy dx if you prefer, equals, I take the derivative of x ln x. X times 1 over x, because that's the derivative of ln, plus ln x. So that's 1 plus ln x. And then finally, to get the y prime all by itself, multiply by y. So y prime is y times 1 plus ln x, but we wouldn't usually leave the y there. We would go back and write that x to the x times 1 plus ln x. So that's what you're going to have to do when x shows up in the base and in the exponent. You're going to have to use logarithmic differentiation. Alright, let's do one more of those. How about y equals sine of x to the 4x. Once again, what you need to notice is that you have x in your base and you have x in your exponent. When you have x in your base and x in your exponent, you're going to use logarithmic differentiation. ln y equals ln of sine of x raised to the 4x. And again, the beauty of those logarithms is it brings the exponent down. So we can write that as 4x ln of sine x. And then we can take our derivative using the product rule and our rules about ln. Taking the derivative, I have 1 over y prime equals, I take the derivative of 4x, that's 4. I leave ln of sine x alone. Plus, I take the derivative of, no, I leave the 4x alone. And then I take the derivative of ln of sine of x. What's the derivative of ln of sine of x? Not 1 over cosine. 1 over sine x, so the sine x stays alone, but it goes to the bottom, times the derivative of sine x, so the derivative of sine is cosine. Alright, so final answer. I would multiply by y, and I would write y prime is sine x to the 4x times 4 ln sine x plus 4x, and I'm going to write that as cotangent x. Cosine over sine is cotangent. Questions on that one?
Where did the cosine x go?
Where did the cosine x? I took cosine over sine, and I wrote it as cotangent.
I thought just the one part.
Yeah.
Think
Other questions?
We just leave it like that.
As far as I'm concerned, and if you'd written it as cosine over sine, I would have been okay with that too. I wouldn't care if you didn't switch that to cotangent. I mean, really, there's not much you could do. About the only thing you really could do is take this and distribute it through, but that's not really going to help anything. I would leave it like that. All right, so you go down to the bank this afternoon and you deposit some money, and they're going to give you some interest. How does the bank figure out how much interest they need to pay you? They're going to pay you almost nothing because the interest rates are so ungodly low right now that you might as well stuff it in your mattress. It's really not doing you any good in the bank, but there's a formula. Anybody know the formula for interest? It's usually A. A stands for amount in the future, equals P, which is your principal, times 1 plus R over N to the NT. That's the formula the bank's usually going to use. All right, so again, A is the amount in the future. P is principal, that's the amount you invest. What's R?
rate.
The R is your interest rate. What's N? N shows up in two spots.
Time frame.
Numbers.
It's the number of times per year. So for example, if your money is compounded quarterly, N would be 4. If your money is compounded monthly, N would be 12. If your money was compounded daily, N would be
0.24 or 25.
actually banks usually use 360. They jip you out of 4 days. You were right. Just guess. They actually do usually use 360, not
Well, that
365.
makes sense, so they don't have to ever change it.
What's their justification for that?
It makes them money and costs you money. That's their justification.
They don't need to.
You ever wonder why banks usually have the prettiest, nicest buildings in town?
Well, I figured that.
They make a lot of money off of you. And T is time in years. All right, so you invest $1 at 100% interest. For 1 year. So if you're going to invest $1 at 100% interest for 1 year, this formula becomes A equals, what's our principal? 1. 1 plus, what's our interest rate? 100%, which would be 1, right? 1 over N, I didn't tell you N, did I? Raised to the N.
T was 1.
Because T was 1 year. So notice this gives us a function which has variable in the base and variable in the exponent. Now, if you have the option, do you want your money compounded quarterly? Do you want it compounded monthly? Do you want it compounded bi-weekly? Hourly? Why? So you make more money. All right, so did I bring a calculator today?
He used it to.
Yeah, it's holding the projector up.
Oh, it's propping up the screen, isn't it? I borrowed somebody's calculator. Alright, so 1 plus 1 over x raised to the x.
I think my graph might be Like the axes might be.
That's okay, I'm not going to look at the graph anyway. I'm going to use a table. So, if our money was compounded one time per year, we make $1, we get $2 in the end because we're earning 100% interest. If we go to quarterly, which would mean we get interest 4 times a year, notice we're up to $2.44. So quarterly is better than once a year, isn't it? Monthly is better. You're up to $2.61.
8,640.
What's that?
8,640
What's 8,640? Is that hourly?
hours in a year.
So if they pay me my interest hourly, which would be 8,640 times in the year, I'm up to $2.71.
That doesn't even help that much.
It doesn't help that much. So what you're saying is, when this number gets bigger, let's make this number like 1 million. So they pay me interest 1 million times a year. The Y value is getting bigger, isn't it?
Yeah,
But is it getting a lot bigger? No. In fact, it looks like these Y values are approaching an asymptote. And what number do they look like they're getting closer and closer to?
2.718 something.
2.718 something, something, something. Anybody recognize that number? That happens to be the number E. The limit as n goes to infinity of 1 plus 1 over n to the n is the number E. So I want you to think about what's happening here. When n gets really, really, really big, what's happening to 1 plus 1 over n? It's getting really, really close to... When n is really, really big, 1 over n gets really, really close to 0. So inside here, we're getting close to a number 1, aren't we? 1 to the infinity. This is what we call in math an indeterminate form. It's kind of like in Calc 1 where we had lots of problems where we had 0 over 0. And we saw that 0 over 0, depending on the problem, we could make it come out to be anything we wanted to. The same thing happens with 1 to the infinity. 1 to the infinity is not the number 1. It can turn out to be any value. Here's an example where it turns out to be E. And later on in this course, we'll study something called L'Hopital's rule, where we will study more functions of the form 1 to the infinity, and we'll see that those answers can come out to be anything you want. All right, so the moral of the story is, if you could ever get a bank to compound the money continuously, the formula would come out to be A equals P to the E, P times E to the RT. And I think somebody said that formula right when I said that. Anybody know the interest formula? Quite often known as PERC. Because this 1 over 1 plus n to the n part, when n gets bigger and bigger and bigger, that's going to get closer and closer to E. So you're going to have E to that R, and then you'll have T. Unfortunately, I don't think you can ever convince a bank to compound their money continuously, because that means that they are paying you the absolute maximum amount of interest that you can earn. And they don't do that. They pay you a low interest rate so that they can take your money and invest it somewhere else at a higher interest rate and make more money. Questions about that?